good morning and thank you for joining me here in my shop. It's April 19th. It's another gray, rainy day outside, so it's not so bad to be in here. And what am I going to do with this radio now? I think I'm going to start in the audio circuit end of things, the output end of things. Examine the circuitry, the parts in there. We're talking about this end of the radio right now. And look for capacitors that probably should be changed out. It gives you 1, 2, 3. Probably these two also probably should be changed out. So what I want to do is first of all get comfortable with the type of output circuit that's in here. It's a push-pull arrangement, so that involves usually 5 tubes to pull off a push-pull arrangement. So and that's what's in here. There's 5 tubes. You could even say 6 tubes, because you could include the detector tube. There's 6 tubes in the audio circuit. And we'll look at that on the schematic. Another thing that I got to sort of keep in mind are these electrolytic capacitors here, the one there, and there's 2 up on top. For some reason the radio is not exhibiting any problem, or at least I haven't noticed any problem with them yet. But you have to be suspicious of those capacitors, I would think. As for the, as I discovered during my operational test yesterday, I managed to screw up one of the strings here and get it backwards, basically. And that's the string that tells you what band you're on. And though I applied tremendous logic, my logic failed miserably, but I could have noticed something had I looked. So here's the string we're talking about. It's right here. And right here, it's coming out of here, goes all the way across. It's one string, goes all the way across. And I brought it in so the strings crossed each other. I thought somehow that was clever. I thought they were avoiding this knob. That's what I thought was happening. But now when I look at it, I don't know if you can really see this, the 2 strings where they cross are in contact with each other. No, that's never done. So had I really noticed that when I put the string on, I would have hesitated and gone, nah, I don't think this is how they wanted it. I'm going to leave the string the way it is, because it doesn't really have any impact on the operation of the radio for now. And I'll just realize that the band indicator is backwards. And I think we can probably handle the situation from there. Okay. You just notice it's another one of those big square capacitors way back under here. Good. Next step is to study the schematic and analyze the way the circuit operates. It's pretty typical of a push-pull output amplifier. Okay, here's the schematic, and the tubes that I'm concerned about, or the audio tubes, are these guys down here, and we can include this one too as the number 1 or the first tube in the audio series. So why so many tubes? So these 2 are driving the speaker, and these 2 are driving these 2. This one is producing a flipped over signal, or a signal that's been that's 180 degrees out of phase with the original signal. So from this tube there are 2 signals coming out. You can think of it that way anyway. A regular one that would match the radio, and one that's been flipped over 180 degrees. And that's going down this way. So that's the purpose of this. They call it a phase changer in this radio. And then this tube is the first audio amplifier. These are the detector diodes. They're in the same tube. They're there because of convenience, not because of any functional advantage of having them here. It's just 1 tube instead of 2. And it's extremely common to find a tube like this in a radio, with the diodes and the triode amplifier here. I guess if you have a tube with 2 diodes in it, it's pretty empty. So why not stick some more stuff in it? So this is where the audio is starting. The audio signal coming out of the radio part of the radio is attached to the grid here, and it's amplified in this tube, and its output is coming out this way. Now this capacitor has to block the DC charge, take it all back. Hold on, this tube's drawn upside down, Jim. They got the plate on the bottom and the cathode on the top, and the heater on the very top. Okay, upside down tube diagram. Then we're talking about this being the plate. That makes more sense. And then we have the signal coming out. Here's a capacitor blocking any DC that's on the plate circuit from going further. So the audio is traveling through here. We get to this voltage divider here. What do we got? We got 400, 100, and 500. So exactly what's going on here I don't know, but they're dividing the voltage. The signal can come out the other end of this and get to the grid down here. So this tube is getting the normal signal coming out. Now the normal signal, it should also be fed to this grid. Yeah, here it is coming from the normal signal line. And then it's amplified, or it's really not amplified in this tube. In fact, it shouldn't be amplified. It should come out at the same strength, which is probably one of the challenges in doing this. Out it comes. A DC blocked by this capacitor. That's two DC blocking capacitors we've come across already. Both of them 0.006. They're probably paper wax capacitors. They probably should be changed. So now we've got the reversed signal. Oh, what's it doing here? Okay, so I'm not quite getting this. So here's the original signal going like this, and coming out of here and going down this way is the phase changed signal, or the reverse signal. Okay, so that's how these two tubes have the same signal but 180 degrees out of phase. Now I believe the biasing in these tubes is done in such a way that any positive, you know what, I'm not going to say. I'm not sure. I won't say what I'm not sure of. Let's just say these produce a large voltage swing output to drive the grid on the output tubes. There isn't enough swing here, and there isn't an out of phase signal here until you've done this thing. Okay, so just put on your thinking cap while you're listening to me, because I think I'm confusing a few things here, but that's okay, because the purpose of this is to get my head straight on this. Again, there's the plate voltage 230 and 250 higher plate voltage here, a low plate voltage here of 100 volts, and even lower here, 75 volts. This is normal to have a low plate voltage on this tube. And I believe, I'm not sure, but I believe the reason is slipping my mind right now. If you have a higher plate voltage, you have a higher acceleration of the electrons, and they strike the plate with higher force, and the result is they can knock other electrons out, and the result of this, especially in a triode, is noise. Maybe I got that wrong, but I think the reason for the low voltage here is to make sure this is a low noise amplifier, because any noise here is just going to be amplified and you're going to show up out here. A little bit of noise added here, you're not going to hear it. Same thing with hums. You know, a little bit of hum, you're not going to hear it, even if it's there. Okay, so that's the basic idea. Signal comes out of the radio, gets detected in the diodes, gets amplified in the triode, gets flipped over by this tube. The flipped over is going this way, the regular is going that way. These two tubes are driving these tubes, which are then feeding, and this is tricky to look at because of this, but these guys will feed the outside of this center tap transformer. And this is where these two tubes' outputs are put back together into one output and then fed through the transformer to the speaker. Okay, I gotta stop and I gotta drink some coffee here. Okay, had to take a little break there and drink some coffee. And my mouth had gone bone dry, so hopefully you didn't hear it clicking and all that kind of stuff. So here we go. Well, what am I going to do about this? Well, the radio produces some volume already, and it sounds okay. It doesn't seem to me that there's a serious problem here. Let's look at how they've biased this stuff. So we'll start with the cathode. So here the cathode. Cathode. Okay, so the cathode there's no resistor or anything in the cathode circuit of any of these tubes. Oh, I'll take that back. Oh, I missed that. 22,000 ohms. The M actually means 1,000 on this schematic. I may get very quiet here because I don't think I'm going to be able to pick this apart. Yeah, I'm not going to be able to follow exactly what they're doing here. You know, on a high level, it's quite simple, as I explained before. You know, these two tubes are producing an output voltage swing that's sufficient to drive the grid and operate these two tubes. And this guy's producing an inverted version of the incoming signal to apply to probably these two tubes. This creates the push-pull effect, where the positive half of the signal assumably is going one way, maybe this way, and the negative going half of the signal is coming through here, and then the negative and positive swings of the signal are combined in the transformer down here and then fed off to the speaker. So let's look at the grids. So we have a plate here with a capacitor and blocking. So I got to find this one here. Any more like that? I just followed the wrong thing, didn't I? Yeah. No. This one. So we got this guy and this guy, and it's easier actually to look at the plates that they're blocking. So you have a plate here and a plate here. So there should be two capacitors. 1, 2 happen to be the same size, 0.006. So we need to find these capacitors in the radio. Now there is a parts diagram. I don't know if I have it here. Do I have it? Here we are. Locations of parts under chassis in the radio, version 1, version 2, version 4, version 5. I've got version 2 here. So we'd want to find the location of these two capacitors, 34 and 29. 29 and 34. 29, that's a resistor. 29, oh, it's hard to read these numbers. Is that C29 there? And C34 right here. So 29 and 34 tucked in right here. Now, this is a little odd. What are these? These are the big filter capacitors. You know, they're mounted up on top. Why are they showing like this? And these parts are shown hidden. These dotted line ones are shown as if they're hidden under this, but this is not here. These two items are out of the radio up here. And I have two more capacitors in this radio. This diagram doesn't match. I have two large capacitors sitting right in here. Okay, let me look with my own eyeballs for these two. And regardless of this situation, maybe it's just a slightly different version of the radio or something, and these two capacitors were stuck up on top where they normally are. It's odd that they'd be under here. It's very odd they'd be under here. It's easier to mount them up on top and get them out of here. So I don't know what they're doing with the diagram. C29, C34 right here in the radio. Okay, let's take a look. They show them as what would look like a small wax and a large wax capacitor. That's kind of what it looks like. And three things kind of splaying out here, and then something at the bottom, and a big thing bordering it over here. Can I remember all that? Let's look at the radio. We're talking about down in this corner here. Here's the big thing bordering everything. There's a capacitor there. That's not a wax capacitor. We obviously have these two big guys sitting right here, but they're probably bigger than .006. Let me get the other camera happening here, because I'll see what we can see with that. Now, unfortunately, the autofocus is operating right now, so this might drive us a little nuts. A little nutsy. Well, so wax capacitors. No, there's no wax capacitors here, or is there? These two guys are quite likely wax capacitors. They're made by mica mold, and as I discovered in another radio, these large square ones, especially when they're really thick, are almost certainly paper capacitors. Could those be the 2.06s? Okay, so we're going to look back in the radio now, kind of memorize what you're seeing. This small capacitor back here, two big ones laying flat out on the surface, a big resistor bordering things on the right. I thought there was another resistor running along underneath. I don't really see it. Okay, no wax capacitors. Those are probably it. Those square ones are probably it. So, yeah, this just doesn't really match, does it? I mean, this is there, but this is not. Location of parts under chassis. Well, that says 450, 545, sorry, 584. I thought my radio was a 583. I got the wrong thing here. 583. So there's 583 written here. But up here, 584. Okay, I gotta get another diagram. This is not the right diagram. Okay, here we go. So, thank you, Radio Museum, for this. They are 101 583-2. This is exactly what's written on the radio I have. So this must be the radio here. Okay, now, is there any significant difference from the last one? I think well, here's the layout diagram. Now, those two capacitors are missing, but the big honkers that are in this radio aren't there. So I wonder if those are added in by somebody else. Now, just in looking, I can see these three capacitors, and I can see this one here, and I see that this one I think is laid in vertically over here. Let's go down to business area. So here's the big resistor, and then it shows 29 and 34 here. And you know what? I think those are those two big square ones, I'm pretty sure. And the rest of these are resistors. They're all resistors. Is that really the case? Yes, it is the case in there. Okay, so I know which capacitors they are, and they're both the same size. And both these guys are responsible for blocking DC. They're very important. And to find out if they're working. And that might be interesting. Okay, there they are. These must be the two that I was looking for. Everything else is a resistor in here except for that little capacitor in the back. Yeah, I didn't see that one. But the two capacitors I'm looking for are the same size at .006, and that's a fairly large size, usually in a rolled wax capacitor, but in this case they've been put into these molded cases, But in there is a rolled capacitor, and it's been squashed, so it fits in a square fairly well. Or it's been wound up in a squashed form, or a rectangular form. I can put it like that. Okay, well, I think what's interesting here is to test this radio out and see what these two capacitors are doing. We should find, on one side, we should find a high voltage, and on the other side, we should not. We'll see what's going on here. Yeah, I think that's worth doing. That's what I say. I say, because theoretically, yes, these are leaking. Theoretically, there's a charge building up on the grid of the next tube because of the leak through these. That's all, and it's probably true. I'd like to do the test and see it for real. But first, coffee. You know that old saying, leave well enough alone, something I very much believe in, for sure. I shouldn't be looking at these schematics so closely. So look, grid, 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 grid. These grids, any resistors off them? Not really. I mean, this one's hooked up into these resistors, but that's coming from the plate here. So what I'm looking for is a resistor on the grid going to ground, as there normally would be, a high value resistor tying the grid to ground, but there isn't one. There isn't one here. There isn't one. Well, they're kind of, yeah, kind of, sort of there, but kind of, sort of there too. Now let's look at another diagram. Not this. Look at this one. Same circuit, same sort of thing. Grids, no resistors going to ground. Look at this one. So over here on this tube, suddenly you see this thing. Now that looks like a ground symbol, and this looks like a resistor, and it looks like it's hand drawn, like an after the fact thing. Somebody came along and drew that in. There's no value, no number, no nothing. What is that supposed to be? And look, this is the radio I have. So I wonder if there's any other handwritten notations in here that might give us a hint as to what this diagram really is. An earlier version marked up and then put out as a new version. Oh, look at this. Chassis identified as that -2. That's mine. It's the same as that, except for circuit changes that eliminate the bias cell. Okay, that's why I couldn't find the bias cell. It's gone. And remove the 39,000 ohm resistor R12, the 22,000 ohm resistor R23. So they figured out how to make this radio with less parts. I guess the large should be what they're saying. The resistor, then the condenser, 15 mega ohm, R17, and R17 and an 82,000 ohm resistor. So here, two things have been added: 15 mega ohm resistor. All these changes are shown in the schematic. Well, how did they show them? Like they just have them on the schematic. Maybe they put little asterisks. Part of T1 in tuning eye socket. Oh, they're talking about a resistor that's mounted inside the tuning eye socket, which is very common. A resistor that almost always is bad in the tuning eye. But again, that's not critical for the operation of the radio. So, okay, that explains a lot. Location of parts under chassis. They put the title there. That's a weird place to write a title. The title should have been written down here. And all these, what I was taught when I was working at Toronto Hydro was anytime you make a map, a diagram, we made a lot of maps with, pencil and a ruler and a piece of paper. We always had to put a border around the outside. If we didn't put a border around the outside, we get in trouble. And why do you need a border around the outside of a diagram like this, like a page border? We just rule it in with a pencil and a ruler. Because if you put this on the photocopier and you miss, you accidentally somehow miss something on the edge, like this, this note doesn't come through. And now you've got a photocopied version of the thing with this note missing. How would you hand it to somebody? How would they know this note is missing? You know, what's missing is missed. Because there's a border, and everything is inside the border, and if you photocopy it wrong, or reproduce it wrong, the border line is missing, and then people know, hey, there's no border on this diagram. How do I know everything is here for me to see? And that's why these diagrams need to have a border on them, but they don't. And so I'm going to do something about it. I'm going to write to the guys who did this, and I'm going to tell them, hey, you better do a better job from now on, because this isn't going to fly here without a border. Okay, so assumption though is we aren't missing anything here. If anything's missing, it's just missing inside my head. And there's no border on my head, although I have to wear a hat. Well, okay, I think we're back to just checking some voltages here, and we can even look at the voltages not only related to these two capacitors. We might as well go a little bit further and ponder what is the voltage of the grid here. Now, because of this, it should be at ground potential. So this is like a cathode. I don't know what this is. What they've done here, they've got the cathode hooked directly to the grid in the next tube. Without that, this just doesn't make much sense. What's here, even with it. Well, with it, it does make more sense, actually. They're simply grounding the cathode and grounding the grid, and the fact that this wire runs like this doesn't mean anything. Well, it does. There's a resistor here. They're taking the signal from the cathode of this. That's what's going on. They're taking the signal. It's like a cathode follower sort of deal here. And this one, they're taking it off the cathode too. Okay, so much for what I was going to say. You know what? I don't really get it. But we're not going to worry about it. 245 volts sitting here, but it's got no way to get over to the grid here. So I think these grids are bound to be zeros. That's curious. Anything else I need to pick up on here before I start wielding the voltmeter? I don't think so. I think I'm ready to wield it. Just before we get going, look at this. I hope this works now. I was able to tune the radio all the way from one side to the other. Uh-oh. Uh-oh. Well, it did it one time anyway. Close, getting closer, getting better. It did work before I, of course, want to show you. Now we need to see this meter over here. So that's what we're going to be taking the readings with. And that's good enough there. Okay, that's good enough. So we gotta turn the set on, Jim. I'm going to turn it on. Switch is on. Power coming. Did I connect the antenna still? No. We need to connect the antenna here. There we go. Wow. Okay. Volume's down. Band is set to broadcast. We're ready to go. I could hear a little filament vibration there when I first turned the power on, which I think is quite common in these old radios. If you first turn them on, you hear a little, I don't know how to describe it, tinkly sound. Okay, first thing we want to try to do is figure out what the B plus ultimately is in the radio. Oh, wait a minute, you're jumping the gun, Jim. We gotta get some happening here. Okay, because I trust the radio from previous, I'm just going to give it the full works. It's going to be 104 volts. There we are. Okay, got the radio working. Should we bother tuning something in? This is the worst tuning radio I've ever, the amount of play in the thing is just horrible. Okay, so we're not going to get too much in here. I know I've got installed it. Oh, look at that. That spring isn't even tight. Well, that's really where the problem is. Oh, it's come off a wheel. It's come off one of those. Okay, hold on. Back the cart up. So it's come off one of these mouse-chewed wheels here, and this is really throwing the tension way off. Remember, don't forget the radio's switched on, Jim. Don't forget this. Got this metal thing I'm sticking in the radio. Well, I hope this doesn't continually dismount because the mouse did too much to it. Betcha that's what's going to happen. No, nothing's moving. Okay, we're not going to worry about that. You can hear some sound. The radio's operating, no doubt about it. I've got it on a decent voltage, 104. Let's go just a touch higher here. Let's say up around 110 anyway. 110. Okay, 110 volts on this guy. Now, looking at the meter here, I've got the meter set for a positive upscale reading. I've got it set 500 volts. So we're going to look for the B+. The B+ was around 250, somewhere in the middle. You might find it right here. Something there, but not any great big one. What about back on this capacitor here? There's the 250. Now, can I get at the big capacitor over here? Ooh, it just does not look friendly to me. It's just a chance there's nothing hooked up to that capacitor, but I can make contact here. Yeah, see there's nothing? So these are the replacements that somebody has worked in, I think. They don't show up on the diagram. They don't show up anywhere. And it's a curious thing that was done up here. So these two guys are in parallel. The bottom of them I can't see, but you can guess they're tied to the chassis, but that's a guess. But the top, yeah, we're only getting 100 volts here. That's not very good. We got 250 on the other one. What's that look like on the schematic? So on the schematic, we have where are they? Where they put the filter capacitors? Here they are over here. Well, they're quite different in how they're set up. One is, did they have a voltage here? Did they write a voltage? 315 volts, 125 milliamps, but the arrow's pointing here. Going back this one. It's a lower rated capacitor, so they're anticipating two quite different voltages here. Can we follow this all the way up to where it says something? Right up here. Wait a minute, that's not going to work. I'm on the wrong line here. I'm following the wrong line. No, I'm not following the wrong line. Goes right. Nope, here we are. So we have 105 volts here, but there's a dropping resistor there, so we know it's more than 105. Look at this. Look at this. We straight to here, 245. That's right off the top of one of these. 245 right off the top of one. Now the other one. Ooh, okay, it's going through the thing, coming out here. Ooh, I got back to the got back to the same line. How did that happen? What did I do? Okay. Yeah, that's just coming off here. So this is the main, the higher voltage one. So what's this guy doing? This guy's also, he's on the same line. It's on the same line. Wait a minute, look at this more closely. Here's the two capacitors. Well, they're not on the same line. They're separated by the field coil. Oh my. So you get across the field coil and the voltage has dropped down to 100 volts. Ooh, that's not good. That's not good. So, we don't have the right speaker here. I have a speaker I grabbed. Just the radio's getting quiet. Why are you getting quiet? I'm scaring the radio and it's getting quiet. I'm noticing a lot more weirdness in here now too. I'll have to show you something and try to remember tube pins to show you some strange tube pins. Okay, that doesn't sound good to me at all. That sounds like way too much dropping on the field coil, and we know it's supposed to be 600 ohms. So is this where the omega thing happened? 600 omegas here. That must be where it happened. Yeah. Thank you for the email. I got an email talking about omegas, and I had no idea. What? I think it must have been this when I referred. Okay. Not fun. So chances are the field coil is a much higher resistance than 600 omegas, and the result is big voltage drop on the field coil, and the result of that is a relaxed voltage all through the radio. Now, is that the driving speaker voltage we're talking about? The driving speaker voltage. So how do the plates get their voltage? They get it through here, and they get it from the far side of the coil. You're coming out of the power supply, going through the field coil, and on the other side, oh my gosh, this means this 230 is down to 100 volts. Okay, well, that's interesting. Let's go look at the actual voltages on these tubes now. Now this diagram's arranged as it is in the radio, in the sense that here's the key. If we can find the key on the tube, we can just go around like this. That's why there's gaps here and everything. And I don't have to flip to another camera to show you this weirdness on the tube pins. So tube sockets, when the tube pin comes through, it comes through into a metal grip, right? If you push it from the top, ouch! If you push it from the top, pins come through like they are here, and they usually come through, I can't really show you, a gripping thing. See the gripping things there? I mean, that's got no gripping thing, but it's got a hook up to it. That's got no grip, no grip. So what's the story with that? There still is some metal down there. I don't know what the story is, what they're trying to do with it. Like here's an entire opening. There's no tube pin, and that's because there's no tube pin in the tube. Same thing here. I don't know. That's a weird thing. I assume these pins are not connected to anything, and then they're just in the open. Yet there's a wire connected there. I don't know. That's just a strange observation. I should put the close-up camera on that just for a moment, just to make sure you can see what I'm talking about. Okay, so that might be a transition I'll miss editing out later. So here we are looking at it. I got autofocus on so we can get a little closer. So I'm talking about, now this radio's on, so I got to be a little careful here. These two pins here, see, they're just sticking out. Likewise, the same thing happening over here with one pin, but it's connected. You can see there's a metal sleeve, I guess that's the right word, sleeve, down there. But it doesn't come up on the tube, and there's a component attached to the terminal that goes to the pin that's got no sleeve. Well, there's quite a few of them like that. You got me. What they're trying to do there, were they trying to save the cost of a sleeve? Yeah, they're trying to save the cost of a sleeve on a tube socket. or there's something more to it. Okay, so we'll start with these two capacitors, which are the blocking capacitors. On the diagram, they are C34 and C29. One side should have some hundreds of volts, and the other side should have some nothings. So maybe the high side is down here. So this is an effect now I have witnessed all my life working on radios. Hear how the volume went down? I'll turn it up a bit. Of course, you can't demonstrate it. What I'm trying to demonstrate is sometimes when you cause a little shock into the circuit, something connects, something disconnects, some tiny little molecular short circuit or something can connect and disconnect, or I don't know what to make of it, but I can't demonstrate it other than it happening when I first did it. Okay, let's get back to reading the voltage. So, okay, 150 volts full scale on the meter. All of that's 12 volts, and the other one, even less. And then on the other side we've got a similar voltage but low. Then none of that adds up. None of that adds up. Let's look at this diagram again here. So the tubes I'm messing around with, I believe, are these two here. These two tubes are these two tubes, and the output tubes are up here. These are the output tubes, driver tubes. Down here's a detector and the inverter tube. The other way around, probably. Inverter and detector tube, probably. Don't touch that stuff, Jim. Get your finger out of there, for crying out loud. Okay, let's be sure of what we're doing here. So if I take this tube, which I believe is one of the driver tubes, and there's the key. And if we count around to get to this pin, we go 1, 2, 3, 4. It's pin number 5. So look on the diagram now, and we count around 1, 2, 3, skip 5. Why, it's a grid. Oh, it's an output tube. Whoops. Same thing over here, though. Well, that's funny, isn't it? These are exactly the same. How they're arranged. So is this. Of course, the same tube. Same tube, same tube. These three are the same tube. Takes a while to, pick up on everything when you're doing this work. That's why I like driving around through the schematic kind of randomly, looking at stuff, because no telling what you might see. So if these are the plates of the driver, let's get to the plate. And the plate is only 3, pin 3. I was on the wrong plate. On 2. No, I wasn't. Mr. Confusion. So I'm checking the grids to look for a positive voltage caused by the leak of these capacitors. That's what I've been doing, and I have found a voltage on either side of these two capacitors. Doesn't seem right to me that you would have a voltage on either side. You're supposed to have 100 on one side and on this one 75, but I didn't get anything like that. Did I? 100 volts? Let's check again. Make sure. So we go down here. Okay, and so on the 150 volt scale, this is 35 volts, and over here, 20 volts or something even less. And then on the other side, where I'm pretty sure you should see a 0, and this would be due to leaks in these two capacitors. It's really out of sorts. It's really out of sorts. Could the leak be pulling down the... No, you can't pull a plate voltage down with a little leak through a capacitor like that. You need a big leak. You need a short. Why? So is it low because the field coil is burning up all the energy in this radio and there's nothing left for the poor tubes to operate with, even though it works. Okay, plate voltage on those same two tubes. Plate is pin 3. So if we come around here, we go 1, 2, 3. I'm on the one, let's go on the 500 volt scale. I'm going to go 1, 2, 3. It's down in there. It's here. Oh, that's nothing. So on the 500 volt scale, that's 90 volts. It's supposed to be 245. Oh boy, oh boy. This means that a lot of power is being burned up in the field coil of the speaker. And the speaker should be getting hot, or could be getting hot. I need to find out and look where that speaker is. It's way back there, man. Okay. Best way to do it is put your hand on it. Well, there's a little bit of heat in it, but that's normal. It's not much at all. It's not enough to worry about. So probably what's happening then is the amount of current flow is being restricted. So you're getting not quite as much risk to the field coil. We just have a very low voltage radio now. Wow. That speaker's my only choice for this radio. It's the only it's the only one I've got. Alternatives are, you have to put in some kind of a field coil replacement, some kind of choke coil. So I didn't do plate on both of them, did I? I just did one. So to do both, I did that one. So do this one. The tube is not in the same way. So this, yeah, I did. It's the same wire. It's the same wire. Uh-oh, something going. Something started sizzling. I can see what it is. It's smoke coming from, probably out of that. Can you see the smoke coming out of that? Let's quickly get my, where's my thermal viewer? Okay, oh, my shop's filling with smoke here. So, I can feel the heat coming off that. That guy fried. Maybe that's a cause of the low voltage. Oh, look at the smoke coming out of him. He's frying up. Took a while, eh? There's my viewer. Here's my battery. I got it right here on the bench. See, I didn't put it where it was supposed to be, and then a panic ensued, and then I can't respond properly. And this is really filling up with smoke in here, and I gotta get out. Don't like breathing this kind of stuff. Okay, I gotta change some settings. Make it less sensitive. Well, there's still smoke pouring out of that thing. Oh! You can't, there, you can see it like that. That red thing there, she's still frying. How come? I got the power cut right off to this radio. It's got no power coming to it. Wow, that must have got pretty darn hot. How hot? I can tell how hot it got. Well, it's only 40 right now. Ooh, something said 78, 90. It was a hot spot. 100. So I'm reading these numbers here, and I know you really can't. So probably the connection into the capacitor, there's 100 there. 100 and, we can get the colors here. We're going to just do this until we're left with where it's really hot. That's as high as I can set my thing. See the top of it. It's the top. 105 still. That's above boiling point. That is hot. Wow. I gotta get out of here because it's really got a bad smell in here. I'm gonna bail. I'm bailing. Okay. So we're going to look into just what this part is doing, and is this the reason why the voltage is low? This thing had to be sucking back power in order to get hot like that. So it was drawing a fair bit of current. Probably shouldn't have been. Of course it shouldn't have been. So this raises an interesting general question, and I'm going to talk about a little bit of history involved too. How hot can these things get and you should still be okay? This thing in particular I can't really talk about, but I can talk generally and historically, because I worked in a power company and I was responsible for the underground power cables, and these are big power cables running at 4,000 and 13,000 volts, no higher than that. And these were old cables. I was working in Toronto. It was an old city, had an old electric system, and parts of the plant were still operating that had been installed in the 1930s. These cables would blow up. Part of my job was to examine cable faults and determine the cause, and so I saw a lot of these old cables. Cables were made with basically a lead pipe with 3 conductors inside, and each conductor has paper wrapped around it, not unlike a capacitor here, but they're not capacitors by any means. Paper wrapped around it. Paper does 2 things. 1, it doesn't conduct. 2, it holds the conductor in place quite firmly. So that's how the cables were constructed. But paper alone isn't enough because there'll be air in amongst the paper, and so you got to get rid of the air. So to get rid of the air in the cable, because you have ionization problems, you fill the cable with oil. Well, you don't really fill it with oil, you soak the paper in oil. Well, you don't actually soak the paper in oil. That's not enough. I was in the plant where these cables were being made. Lead sheath paper insulated cables, commonly called PILC cables. There's a plant in Toronto that was making them, and I happened to be there, and lucky enough, I asked the guy to give me a tour, and he did. And we got in it's a big factory with big heavy machines. I won't go into all this. It's fascinating for me to see how they actually make these cables, but there is a stage where the copper conductor, there's like 27 conductors bundled together to make 27 wires bundled together to make one phase conductor, and then they want to wrap paper around it. Then they want to take 3 of these paper wrapped conductors, and then they want to kind of bundle them together a little bit, but they don't want to put the lead sheath on it yet. So that's what you've got. They want to get the oil into it now. So how do they do that? So it had a huge vat and sunk into the floor of the factory. So what you would see if you walked up to it, about stomach high, is the lid. The lid was huge. It probably had 250 big bolts all around it, all the way around the lid. And the reason was they wanted to pull a vacuum on this gigantic tank. Now, you've seen trucks driving down the road carrying cable. I'm sure you've seen it with the great big reels of cable on these trucks. You've probably seen it or seen them along the side of the road and stuff. They had a crane lift a whole reel, wooden reel, full of this unsheathed paper insulated cable down into the tank, no oil, down into the tank, seal it, bolt it all down, and then draw a big vacuum on it. The objective is to draw all the air out of the paper, but it's not just air touching the paper. The paper is made of fibers, and the fibers are hollow. So there's air inside the fibers. They had to get that air out and replace it with oil, or the stuff was never going to work well. So you draw a big vacuum. When they get the vacuum down to whatever it was, they then allow oil to go in. The oil then flows in. There's no air in preventing it from soaking into the paper, and that's why these are called PILC, paper insulated lead covered. And if you ask about the paper, they'll tell you it's impregnated with oil. So they don't say it's soaked with oil, they say it's impregnated, and what they're talking about is oil going up the paper fiber tubes. So that's what's inside these cables. Now, in the early days, say around 1900 or so, as they began to actually manufacture and start operating these cables, and there's a really interesting history of early experiments with trying to run electricity at a high voltage down cables. A lot of failed experiments, though. But one of the issues that came up was, how hot can you let this cable get? You see, in electric systems, the issue is not really how much current you can put down something. The real issue is, how hot is that something getting? That's what limits the current, not the thing itself. It's the temperature you want to operate it at. And why is there a limit? Well, as the temperature goes up, there comes a point where it can cause degradation of the materials used in whatever it is you're heating up. What are those temperatures? How would they know? They want to operate these cables, like build them in a factory, put them into service, wait 30 years to see how it works out, take a guess at what the temperature could be, then you work back and develop or determine the current flow that will generate that kind of temperature rise, and that becomes the limiting current on the cable. But it's not really current, it's temperature. So what they did was they said, well, look what's in these cables: paper and oil. What do we know about paper and oil? Well, we know that if you heat paper up to 90 degrees and leave it there at 90 degrees C, that's just below the boiling point, you can come back years later and the paper will still be pretty much the same. But if you heat it up to like 110 and come back a couple years later, the paper will be carbonized. So there's some limit in there. So they decided, okay, we're going to pick a standard, we're going to operate the system that way. This is like all over North America, maybe all over the world too, I don't really know. I guess the same problem's occurring all over the world at this time. We're going to pick a temperature, we're going to operate the cables there, we're going to observe the result, and then we can decide if we can operate them more hot or if we're already operating them too hot. It's a very complicated story, because it's not just how hot they get, it's how much the temperature changes each day because of expansion and contraction. Wearing out the electric system under the streets. Literally, cables are expanding and contracting a half an inch. That causes movement. That movement actually wears out the cable in various ways, not the least of which is the flexing of the cable causes the lead outer covering to crack. Just like when you bend a coat hanger wire until it finally breaks. Same thing with lead. You bend it and it starts to form breaks at the crystal boundaries in the lead and whatnot. Eventually you get oil leaking out, or more importantly, water going in, and boom. That has nothing to do with how hot you operated the cable. It has to do with the temperature range over which the cable is operating during a 24-hour normal cycle. So, like for instance, if a cable is feeding a factory and the factory shuts down at night, then the cable cools right down. The next morning they come in and turn the machines on, the cable heats way up again, maybe up to 70, 80 degrees. Expands and contracts. Eventually something bad's going to happen. So what's the story here? Well, this contains similar materials to a power cable. As far as I know, I'd have to tear this apart to really know for sure what's in there. It's electrolytic, so it's not the same as just an ordinary paper capacitor. But I thought this was a good time, considering what happened here. And also, I've got this device. I can measure the temperature of anything in here. How do I know when too hot is too hot? So there's two ways. One is the story I just told you, 90 degrees. For radio like this, I would say much lower. I would say 80, 75 degrees C, and you've probably got something you got to deal with. You can think of it another way too. You take it down to, say, around 50 degrees C, and that's too hot to touch. So do you want things in your radio that are too hot to touch? Probably not. So that's the whole story, that as I understand it, about how these things were determined in the early days when there was no real science and no experience and certainly no long-term operating thing. Guess what though? When I was working at Toronto Hydro, the 70s, 80s, 90s, 90 degrees C was still the number that was being used and the calculations for the ratings of the cable. Yeah, I could keep talking, but I shouldn't. What are we going to do about this capacitor? First, we're going to find, is it still hot? Oh, it's still warm. It's still got heat in it. We're going to figure out what this is. So one side is grounded. I can see it. Grounded. The other side is connected to pin number 8 on the rectifier tube. Pin number 8 on the rectifier tube. Okay, let's see what's going on. Pin number 8 on the rectifier tube. Number 8 on the rectifier tube. So here we are. So this is the this is pin 8. That's a capacitor right there. 25. So either that's the original. Oh, we can find out, can't we? Either that's the original. Yeah, we can find it just by going down here and looking for up in the top right corner. Oh, they didn't show this. Like the rectifier. What am I doing here? This is the right radio. The rectifier is sitting up here. And the capacitor is sitting right in this area. They didn't show it. Why wouldn't they show that? Why did they leave all this out? What are they thinking? Or I mean, here it is here, but it's physically sitting right here. And the capacitors, there's a tall capacitor no longer connected, and right beside it is this other capacitor. Well, there you go. So they replaced the tall capacitor with the one that just cooked up. That's what happened there. Kind of like, why would they do this with this diagram? They show you all this stuff, but then not bother with these over here. You know, they're not showing the other capacitor sitting here. But it's sitting right there. They're showing all the parts around it, but they don't show the actual capacitor. It's weird. What are you trying to do? Okay, so we think this is the guy here. I'm going to cut it out and we'll take a look at it and see what we got. Now, what would happen if we just let this thing go? If I had gone upstairs to fiddle around with my cat or something, and just left this thing operating, ultimately, this would have produced a huge amount of smoke. And we would have noticed it all over our house, I'm sure. And the short's only going to get worse and worse, and more current. If it produces a flame, if it should get to that point, the flame itself is conductive. The whole thing's out of control. At what point am I going to blow a fuse? Somewhere in there, I could blow a fuse and have a fuse right here, just in my hand. Smaller fuse, and there's a circuit breaker over there, and then I got my house breaker too. So let's take a look at this. There's nothing on it. It doesn't say a thing. Big dent in it. That's not good. So where'd this come from? What is it? This doesn't say a thing. You can see where the junk was coming out of the top there. Well, that's not good. So we have no idea what this was. And was is the word. Okay, so I'm going to put in a nice, new, reliable capacitor. And how big should it be? 25 at 450. At 450. That's a stretch for me. Okay, I'm going to dig one up. Over the years, by hook and by crook, I've managed to collect quite a number of parts for doing old radio work. And here's some of the capacitors that I acquired. Couldn't even tell you how. Panasonic capacitor. Sounds like something from a transistor radio. Yeah, it is. 35 volts. Yeah, it shouldn't even be in the box. There. But I'm not going to go through all these. Here's what's this? Old looking Mallory one here. 38 motor starting capacitor. Yeah, this great big honker. What's he doing? Wow, that's a beast. I have these. I've never really looked through them that carefully. 370 volts. I can't read the capacitance, but 70C. See, they put the temperature on it. 70C. 35. Looks like 35 microfarads. We're not going to use any of these. I'm not going to have. I'm just showing them to you. Try to impress you with all the stuff I have. Look at this. There's a whole pile of them here. A lot of these have never been installed. 300 volts, 250. Oh, that's got solder on it. Right, so I don't think probably any of these are really sensible for putting into a radio. I just have them, and that's about, right now, it's about the most value I'll ever get out of these, right there, showing them to you. But I have got a couple of suitable possible capacitors. I got this one. It's a 50 microfarad, so it's bigger, at 450 volts. This one's also the same, 450, 47. This one looks like it would fit. Actually, both of these would fit. Now, probably pretty safe to. So this is still warm. This got to be the negative side or the grounded side, and this would be the positive side. So we would want to put this, it's pointing to the negative terminal. So we would want to put it in like that. Could even stand it off because the wires are long. Why would we want to stand it off? No reason. I think I'm going to put this guy in. Yeah, it's 50 instead of 25. It's double. Wow, double. It shouldn't really matter. Let's say I pull a heavier current during charge up for a second or two. It's going to pull it maybe through the field coil, but maybe not. It's going to pull it through the. It's going to look like a short circuit, a persistent short circuit to the rectifier tube. 25, 50. This is going in. I don't have many options, so that guy's going in. Okay, good. Hey, maybe they'll raise the voltage. Okay, come on back. You have the new capacitor in there, soldered in nice and stiff. I did leave it standing off a bit from the tube socket here, because this is the rectifier tube. The socket gets hot. The heat's going to go up the wire. That could be the reason why this first capacitor eventually failed. It was actually repeatedly heated by the why it failed early. Everything's going to fail sooner or later, isn't it? That's a sad thought, isn't it? Everything's headed for failure. Okay, so now we would check and see what's happened to the voltage in the radio, bearing in mind that if this was dragging the voltage down and that's gone, now the voltage is going to be much higher throughout the radio, so other stuff could start taking its turn at smoking. It's possible. Or if the voltage really goes up from, say, 30 to 250, wow. Well, who knows? So I think I did take a voltage test over here and got a low number when we were doing this earlier. I didn't really think hard about it. Okay, let me plug it back in. Okay, with the dim bulbs in first. And standing back. Yes, I stood back. I have this enormous, it's true, annoying habit of getting everything backwards. I don't know why, but... Okay, so we're going to put this on 500. I got to change the camera so you can see the meter over there. 500 volt scale, so full voltage should be pretty much straight up. That was weird. So we're supplying the radio with a very low voltage. What's weird is I put the voltmeter on there and the voltage was going down at the time I did. Well, you know what that is? That's the tubes coming on, drawing current. Okay, so we got to give this guy the full works here because 75 volts is not going to do it. I'm just trying to think, should I keep the dim bulbs in the circuit or not during this? No, that's my decision. Okay, so we're gonna hit this radio. I'm gonna turn down the voltage a little bit. Hit it with a rhythm stick. 97 volts. Oh, radio's come on. So we're in the operating range. Let's go a little higher here. Up around 110. What do we got? Ooh, look at that. It's all there now. So let's look over here. So we're supposed to get 100 on one side or 75. 100 or 75 on one side and should be nothing on the other. It's more sensitive. 15 volts full scale. Ooh, hot diggity dog. Ooh, lots of positive voltage on that side. Let's put this back down to 150 is the proper. So we're in a tiny voltage here of 10 volts. 12 volts, I don't think it should be there. Now we're going to look on the other side. Ooh, it's not much more. Once again, there's more there. Could it be the case that these capacitors are leaking and that's drawing down the supply voltage right there? Interesting question. Because the voltage should be 100 and the two voltages, 175. So making a more accurate reading here, that's 50 volts. Watch what you're doing, Jim. And that's 25 volts, so it's way off. So there's something more going on yet. And I think I'm going to call it quits for today. Because, you know, burning up one part, that's a pretty good day's work, I think. I don't think we have to burn up. I think like one part a day burning up, that would be pretty good. So thanks a lot for watching. And tomorrow we'll continue back on here and wait for other stuff to catch fire and burn up. And I better turn this off right now before I forget. So thanks again for watching, and see you on the next video.